Hello, you should hear me and you should see the desktop. Is everything still okay?
Yes.
Yeah, okay, great. Thanks. I'll just pull up some windows. Okay, so we're going to pick up where we left off on Tuesday, talking about higher order functions. Specifically, we're going to pick up where we talk about this map, filter, fold. But first, let me show you the homework assignment. It's up there now. Okay, so doesn't say much in here because the real instructions are in the uh, an ML file in the zip file. So let's download the zip file. The problems are described in this SML file. Okay, so just show you real quick. The first four problems are like what we've been doing for a while. I give you a type, and you write a function that has that type. And these are higher order types. And you can make the function as simple as you want. You don't have to do anything complicated. Well, they're not very complicated, but you don't have to make the functions real general or anything like that. You can just make it as simple as you want. Just make a function that has that type. Okay. So you can't ignore parameters, for example. You can't just use some of the parameters and not use other ones, because then the function won't end up with this type. So you can make the function as simple as you want. It just has to end up with that type there. Okay, so there's four problems like that. Then there's a couple recursion problems, but recursion using higher order types. Okay, so these are functions that are on lists, but they have a higher order type to them. So they're similar to the recursion problems you've done before, but this time with there's a function that's going to somehow be used on the list. Okay, right. So um, there's two of those. There's two recursion functions, two recursion problems. Okay, then the rest of the problems are from the textbook. They're from the end of chapter 11. Now, these problems are kind of weird. I can't really explain them to you yet. We have to finish what we're talking about on map, filter, and fold, because these problems use those. But make sure you read the directions in the textbook about these problems. And the the relevant stuff is right here. This is the chapter. And for these problems at the end of the chapter, make sure you read these directions real carefully. These directions pertain to these problems. And I assigned you I think 6 of these problems. There's a lot of them. They're real interesting problems. There's 20 some of them in here. And I think I gave you 6 of them, 5 of them only. Okay. 7. You you do 10, 14, 15, and 16 from the chapter in the book. Okay. Okay, so this is chapter 9. Okay, so I gave you 5 of these. There's actually over 20 of them. There's a little over 20 of them in here. Okay, they're real interesting problems. If you like this style of programming, these are really good exercises to do all of them. Because what's interesting is every single one of these problems is supposed to be solved with one line of code. That's actually what this explanation up here tells you. You're supposed to solve every one of these problems with a single line of code. And this is one of the beauties of ML. You can solve actually fairly sophisticated problems with just one line of code. And you'd think that one line of code would be easy, that people measure programming by thousands of lines of code. But in a language like ML, quite often one single line of code can actually solve a fairly good sized problem. So every one of these is to be solved with a single line of code. Okay? But the single line of code will make use of one of these higher order functions: map, fold, reduce. So that's the trick, is you're going to use a kind of a big hammer to write each line of code. Okay, so there's 5 of those then. So there's a mixture of problems in this homework assignment. Like I say, the first few are I give you the type and you have to give me a function that has that type. It can be as simple as you want. You just have to cook up a function that has that type. Then a couple recursion problems, and then these one-line problems out of the book, where each one of these is just one line of code. Okay, each one of these is solved by a single line of code. And there, I gave you some tests in the homework in the folder. I do a little bit of testing of your solutions. So like in the previous assignments, after you finish your code, you could run these tests. Either you could copy these tests into your code. Well, when you turn in your homework, don't have tests mixed in with your homework. Okay, so like before, don't mix in tests with your homework. But when you're doing the homework and you want to test your code, you can either run your homework and then run the test file, or you could like just put your solution from in here into ML, then copy one of these tests from in here into ML. Whatever works best for you. But don't put your tests in here. And this is a minimal set of tests. I just kind of typed in like a pretty small number of tests in here, but I think they're probably good enough, but they're a pretty minimal number of tests. Okay, so I give you a few tests for these problems. Okay, so the homework assignment is due 2 weeks from today. Okay, and so now like the hard part of the assignment are those one-line problems. To do those, we need to talk more about filter, map, and reduce. And that's where we left off in class, just at the end of class on Tuesday. So let's go back to where we were. That was this file here. Okay, we did the map and the filter, and we need to talk about the two folds, fold L and fold R. Now remember, map has that signature. Okay, and if you think, okay, you've got a function from A to B, and you're given a list of A's, and you need a list of B's. The easiest function that just had that signature would pull one item out of that list, apply that function to it, and take the result and put it in a list as the output. Okay, that would be an easy function. So if you wanted a function just to have that signature, I could do it this way. I could say map of x's, well, map of h on x's will equal h of the head of the x's. Oh, but then I have to put that in a list, so I'll just wrap it in a list. Okay, all right. Now let me check. Let me start up ML. Now, like for the homework assignment, it's okay to find the simplest kind of thing that has that signature. Let's check that that actually has the signature. Whoops. Oh, I always forget. I have to put the word fun in front of this. Okay, check. That has the signature, a function from A to B, a list of A's, and a list of B's. Okay, but I just took, and another way to write that would be if I didn't write it with pattern matching there. That's not really, so let me write it with pattern matching. The function map on where I take H. Well, what if you give me the empty list? If you give me the empty list, I don't even care what this function is. I'll just give you back an empty list. And I'll satisfy this thing here. So if you give me the empty list, it doesn't matter what the function is, I'll give you back the empty list. On the other hand, if you give me a non-empty list, map a function on a non-empty list, I'm going to do this. I'm going to keep it simple. The simplest thing to do is apply the function to that thing at the beginning of the list and wrap it in a list. Okay. So there's one step more sophisticated than that one was. This one didn't use pattern matching. And no empty list case. Okay, I'm not using pattern matching and no empty list case. Okay, here I kept it simple still. I've got the pattern matching and the empty list case, but it's still, I can check that this has got the right type. Okay, a function that takes in a function from A to B, a list of A's, and gives me a list of B's. Okay, but I didn't, but now, what you would really want to do is use up everything in that input list. Okay, so now you think, okay, now the more interesting thing is to use everything that's in that input list. Okay, so what should I do? If I want to then that's where the real definition comes in. The real definition was to take this guy and put him in front of, well, just do recursion on the rest. Apply him to the next item in the list. See, here we applied H to the first item in the list. That's good enough to get the right type signature, but we're leaving the whole rest of the list behind and not doing anything with it. So the only thing left to do is just to go work on the rest of the list. After we've applied H to the first item in the list, we cons it on to apply H to the next item in the list, then recursively apply it to the next item in the list, then recursively apply it to the next item in the list until the list is empty, and then you don't have anything to give out. And on this line, I can simplify it. If the list is empty and I'm giving you the empty list back, it doesn't matter even what the function H was. So if I want, I can put a wildcard there because notice I'm not using H on the right-hand side. So I might as well just not point out that it's not important what it is. Okay. So you can, if you think in terms of types, you can build up to this definition of map by thinking, well, what's the most basic thing I could do to have that type? And what's a little bit more sophisticated? And then once you got this idea, it's just it's not very much more to go say, and then I should process the rest of the list. Okay. Kind of the same thinking goes for filter. Okay. Let's think about how, if we think of it from a point of view of type. Okay, we want a function that has this type. It gives us, it takes in a list of A's and a Boolean function from A on A. So it takes in a list of A's and a Boolean function. And we're supposed to put out another list of A's. Okay, so fun filter. Here's that Boolean function. I use the letter P for Boolean functions because usually they're called predicates. That's the fancy word for Boolean functions. Okay, if you give me a list of X's, okay, well, if I just give you back the list you gave me, that's simple. But then since I didn't use P, it's going to tell me that P has type A, not function from A to B. I've got to somehow make use of P for ML to realize it's there. So let me apply P to the head of the list. Okay. But now I'm returning a Boolean. I'm supposed to return an A list. Okay. Now I have to think a little bit. I'm pulling something out of the list. That's an A. I plug it into the function, so now I'm using the function. But now I get back a Boolean. Now but I'm supposed to produce an A list. So then I start thinking, well, this Boolean's going to be either true or false. So let me think. If it's true, then do something else, do something else, then I'm done. Okay. Now I have to produce I could produce an empty list here, an empty list here. Okay. But on your hand, if this is true, why not just put the head of the list in there? Okay. Yeah, you could say the same thing over here. At least here we're doing something. This kind of makes sense. We've got a Boolean function, so we should do one thing or the other thing. So pull a thing out of the list, apply the Boolean to it. You get true or false. Then do one thing or the other to create an output list. Well, the only things that make sense are either use the item we just tested or not use it. Use it in the output list or don't use it in the output list. Okay. All right. And let's check. This is going to be this will have the right type. Oops. function that takes in a Boolean, a list of A, and produces a list of A. Now, the way I've written it, filter of, okay, here's a simple function. Function of X goes to X equals 0. I'm just going to check if a number is 0 or not. There's my predicate. You give me a number and I tell you true if it's 0, false if it's not 0. Okay. And then I'll filter the list 1, 2, 3, 0, 4, 4, 5. Okay. But okay, I got the empty list because 1 was this. It only processed the first time in the list. If I do that again and I put 0 at the beginning of the list, then I'll get the 0 out. But it doesn't look at the rest of the list. Well, why not just keep stepping through the list, keeping the things that make the predicate true and throwing away the things that make the predicate false? Okay, right now we have essentially what would be the core of the function, because that just we did that just to satisfy this. Now make it like here's making it step more sophisticated. Notice that this thing doesn't handle the empty list. So far, if you give this guy the empty list, throws an error. Okay, so make this thing a little bit better. Filter a predicate on the empty list. Well, there's just nothing to filter. There's nothing to do. So just give out the empty list. And it doesn't even matter what the predicate is. Okay, and then use pattern matching. Filter. We'll just do the same dumb thing. P on X in front of X's. Okay. Oh, actually, remember up here, we didn't even use the X's. When we were just only using the first item in the list, I should just point that out to a reader by saying X in front of some other stuff, and I don't care what that other stuff is. I'm only using the thing at the front. When I'm keeping it simple, so when I'm doing the simplest possible thing, I don't even use the rest of the list. So back here, I'm just going to use the first item in the list. Because that's all we did here. We only used the first item in the list. And then it's if the predicate on the X, then if the predicate on the X is true, then put X in the list, else return an empty list. Notice how the function becomes a lot simpler to read when you use pattern matching. Okay, it's a lot easier to read. Now, so this one just is this one with the empty case thrown in and using pattern matching. Okay, and I can check this one's still the same as the one we just did. Okay, can do the same test. Now notice that now filter on the empty list. I'm sorry. Filter on the empty list. Let's see. Oh, it won't work on the empty. It doesn't know enough about the empty list. Let's see. Let's see if I make sure I typed that in correctly. Let me restart. Okay, so here's the one. If I didn't make any typing errors. Okay, has the right type. Okay, filter. Okay, my predicate was the function that takes in X and gives you back if X is equal to 0. Very simple predicate. And I'm going to apply it to the empty list. Yeah, and I got back the empty list. I must have typed in something wrong before. I must have just, I think I just typed in too much stuff and got something messed up. Okay, so now it works on the empty list. And if I give it the list 1, 2, 3, 0, 4, 5, 6, it's going to give me back the empty list. And it only looks at the first item in the list. So if I put 0 at the front of the list, it's going to give me back 0 in the list. Okay, so it's finding the 0. It's supposed to find the zeros in the list. Okay, what this is filtering the numbers that are 0. So this really should have been finding all the zeros in the list. You'd like it to find all the zeros in the list. Okay. Or if you change the predicate to be not equal to 0, you could say all the non-zero items in the list. Okay. So how do you make this thing go through the rest of the list? Well, that's what it does down here. It's a little change now that if the predicate is true on X, instead of returning X by itself, put X at the front of, we'll filter the rest of the list. So instead of putting X in front of it, notice that you can write that as, that's the same thing as saying that X const onto the empty list. This is a slightly fancier way of saying put X in the list by itself. What we're really going to do is say, well, no, we should cons X not onto the empty list, but the filtered rest of the list. Okay, so with a little bit of switching of our thinking, instead of just putting X in the empty list and returning it by itself, we put X in front of the filtered rest of the list. Similarly, if this is false, instead of just returning the empty list, let's go ahead and filter the rest of the list. Okay, so replace these with filter the rest of the list. And then you go from the really simple version to the true version. So you take this super simple version, and all you really do to make it the true version is say, don't just give me back X in front of the empty list or the empty list, put X in front of the filtered rest of the list, or give me back the filtered rest of the list. Okay, so the type kind of guides you to the right answer, from really trivial version to slightly better version to, well, it's not a big jump now to go from the slightly better version to the correct version. Okay, if the type actually guides you through writing the code, that's kind of what's really kind of neat in this style of programming. There's nothing like this in the world of Java or JavaScript or C++. This is what's unique about the world of functional programming. If I give you a type, you can write a function with that type. Now, if you just match the type, you'll probably write too simple a function. But then with a little bit of extra work, guided by the type, you can actually get the correct function. Okay, the type has a lot of information in it, way more than it would in C or C++ or Java or JavaScript. Okay, it's not even easy to explain why this is the case, but it's a very known fact about this style of programming that the types matter a lot. The types are very much a guidance in how to program. This has been C++ is the default language for writing things like sophisticated programs like compilers and operating systems. But C++ has got a lot of problems. So it's being replaced now by the Rust language. Okay, the Rust programming language. One of the key things guiding the Rust programming language is to use types the way we're learning them in ML. Okay, Rust, Microsoft is starting to switch to Rust. I mean, it's not unreasonable to think that in a few years, they'll start, Linux is, parts of Linux are now being rewritten in Rust. Microsoft has announced recently that it's going to make a big push. It joined the Rust Foundation. Okay, it's starting to work on it's starting to use Rust more and more. Microsoft is adopting Rust. Microsoft joins the Rust Foundation. And Rust is trying to be as fast as C++. At the same time, it kind of looks like ML, kind of, okay? Yeah, so it's trying to be it's trying to move into that direction, but still be as fast as C++. And the key is the type system. ML has adopted, well, one of the two key things. There's a couple key things in Rust, but one of the key things is Rust has adopted is ML's type system, not C++'s type system, ML's type system. Okay, but they're trying to merge ML with super fast code to end up with a really modern programming language for writing device drivers and things like that. I mean, that's probably one of the first things you'll start seeing written in Rust in a few years. I'll bet I wouldn't be surprised at all if companies start writing their device drivers in Rust, because device drivers tend to be a few thousand lines of code. Windows is millions of lines of code. They probably will never completely rewrite Windows in Rust, but device drivers would really benefit from being rewritten in Rust. And I bet most companies could probably in a year or so, with a couple of engineers getting some training, they could probably start rewriting the GPU drivers, the network interface card drivers, the hard drive drivers in Rust. And they would probably end up making Windows way sturdier that way. Because most of the time when Windows crashes, it's because of problems with drivers. Okay. And what we're seeing here, that from the type, you can be led to the code. That's one of the beauties of this. And that's one of the things that the Rust people want. Yeah, they want Rust. People, when they're learning Rust, are taught write your types down first. Okay, write your types, then write your tests, then write your code. Okay, and that's kind of the way you think in Rust: types, then tests, then code. Whereas in Java, you're supposed to write your tests first and then your code. You can't write your types first. You write your tests and then you write your code. The types really don't play any role. But with Rust programming, a lot of people take a point of view of what are my types are going to be. And then as you write the types, you think what the function should do, but you write what their types are. Then you think about what you would do to test your code to make sure it's correct, and then you start writing the code. Okay. Now let's go to a slightly harder one. Okay, let's do fold L. Okay, there's the final answer. Let's see if we can build up to it. This one's trickier than the other ones. Okay, so I'm going to define the function fold L. And at first, I'm just going to be willing to get anything that has this type. I want to first just get something simple that has that type, and then see if I can build up to the full-blown version. Okay, so this function has a fold L takes it a function first, and the function takes in a pair of A, B, and gives us out a B. So the function takes in an A thing and a B thing and gives us back a B thing. Okay. Then the function takes in a B thing, and it takes in a list of A things. So notice that the function takes in one B thing, a list of A things, and it's also produced one B thing. And it's given a function from AB pairs to B. Okay, so let's just start playing around with it. There's our H. That's the function that takes in an AB pair and gives me back a B. Here's a B item. Here's a list of A's. So one parameter, another parameter, another parameter. Now I need to produce a B item. Okay, well, X is a B item. X is that B item. But what's wrong with this? Why do I even not even want to? Yeah, I don't even want to check this because it's not going to have the right type. Why not? It's producing the right thing. It's producing a B.
You aren't using the function, and it doesn't know that the
It
Y's
doesn't
is
know.
a list.
Yeah, it doesn't. Yeah, I'm not using the Y, so it doesn't know that that's a list. I'm not using the H, so it doesn't know that's a function. So ML's gonna. ML will accept this, but it's not going to type it the way I want because it doesn't have enough information. So it just thinks it's a function from A, B, C to B because you ignored the first parameter, you ignored the third parameter, and you just took the middle parameter and put it out. So B went to B, and you ignored the first and third parameters, so they're just an A and a C. Okay, so we've got to make use of this function somehow, and we got to make use of something out of this list. Okay, so let's think. How can we get a B item if we use this item, the function, and something out of this list? Well, just take this item, put it in that slot in the function, take the head of this list, put it in that slot in the function. So go over here and say H of Okay, now a pair. H takes a pair. What's in the pair? Well, let's see. I need an A thingy in the first part of the pair. So I'll take the head of the Y's. There's an A thingy. Now I need a B thingy in this function. Well, that's the X parameter. Okay. No, that should work. That used everything, and this should have the right type. The function from AB, an AB pair to a B. I'm using the function on there's the AB pair. I'm using the pair notation. The first item in the pair is the head of that list of A's. And the second item in the pair is that B thing. Okay, so this should work. Let's make sure that I don't think we could do anything simpler. Okay. Well, let's see. We didn't quite get, we didn't still quite get we have a type that's a little bit more general. We have AB to B. Here it says AB to C, a B, and an A list goes to C. Let's see. Did we miss something? It's got the output here is a type C instead of a type B. Oh, okay. Okay, let's go back. Okay, here's what's happened. There's nothing in the way we've done this to say that the output of this guy really is the same as the input here. See how this output is supposed to match this input, but we've never paired the output of this function with a B thing. Okay, so let's do something. Let's change that. Let's create. Let's see. Oh, I know what to do. Let's handle the empty list case. Let's handle the empty list case. Let's ask what to do if we have H, X, but nothing here. Okay, if you give me a function, you give me a B, you give me an empty A list, and I'm supposed to produce a B, what ought I do? Okay, again, I'm given the function, I'm given a B item, an empty A list, and I have to cook up a B item. What should I do? Here's that function. Here's a B item. Here's an empty list. Now I have to produce a B item. What should I put here? It's really easy. Function.
Just the X?
Just the X. Yeah, because X is a B item. So let me just cough it back out. Just cough out the X that I was given. Okay, now let's check that. Now, so we used a little bit more of this type. I actually thought, well, let's think about if this guy's an empty list. So I used a little bit more of that type, and I think now we'll have the right signature. Yes, now we have the right signature. Notice we're still ignoring the rest of this list. So that's the sense that we haven't really finished this function, but we do have the right type now. And this what we've done so far is a big chunk of what fold should do. So we're actually pretty close to the final answer, just trying to get this type signature here. Okay, so we have a function from AB pairs to B's, a B, and a list of A's, and we're giving out a B. Okay, and if I wanted to, I can point out that here, in this case here, I didn't use what H is. So I might as well just say, oh, it doesn't matter what H is because I didn't use it. It's entirely up to you whether you think it's nice to put the H there or it's nice to put the wildcard there. I prefer to put the wildcard there because I think it tells the reader that I'm not using this parameter. On the other hand, putting the H there kind of help, the letter H makes people tend to think of functions, F, G, H. So, you might think, well, the letter H helps somebody remember that that's a function input, but it's also down right here. So there it reminds them that it's a function input. It's kind of, it's one of those style choices that people can argue about a lot. Okay. Is it better to use a wildcard whenever you have a parameter that you're not using? Like here, the parameter is not being used on the right. Some people will say yes. If the parameter is not used on the right, it should be a wildcard. And other people say, well, the parameter helps people read it too. And in a sense, there's a little bit of help in seeing that it's a thinking the input's a function, an item, and a list. And here I'm coughing back out the item. Okay. All right. So
I have a question.
yeah.
So if one of your parameters is a function, like how you have H, do you always basically define that function on the right-hand side?
No, you use it on the right hand side. It's not you're not defining this function, it's given to you. See what I mean? You're not defining H. H is going to be given to you as a parameter. Back over here, I killed off that path. Remember oh, well, that's right here. No. Yeah, right here. See, there was the function H. See how it was given to filter? Yeah. See, the function H was given to filter. It wasn't defined by filter. And then I could give filter any predicate function. I could give it any Boolean function. Okay.
I guess what I'm asking is, like, on the right-hand side, you're sort of like explaining what the parameters for H are.
Yes.
So I guess define is not the right word, but I guess my question is, would you always do that on the right-hand side and never on the left-hand side?
No, because I have to call the function. The left-hand side is defining what the parameters are. Think in terms of like math. Here you define what the inputs are. Here you say what to do with them. Do you ever write that? F of y squared.
Okay, yeah, that makes sense.
Yeah, see, you don't do something on the left-hand side. You're just saying, oh, I got an X in and a Y in and a Z in. And then on the right hand, you say, oh, here's what I do with the X, here's what I do with the Y, here's what I do with them. Okay, like in this case, I could define a higher order function here. And then I'm going to take H of X and add it to H of Z. See, I use H on the right-hand side. Yeah, I could take H of X times Z. I could take plus H of Z squared. So here I list what you're going to give me. Here I use it. Now, what function is H? Well, down here, somebody will call it and say f of 3, the squaring function, and 5. So now I'm calling f with x is 3, h is the squaring function, the function that takes in x and gives me back x squared, and z is 5. And now here I'm calling f with 3, the cosine function, and 9. Okay, or I could call f with 0, the logarithm function, and 8, something like that. See, that is the fun. Notice how why did I write the squaring function that way?
Would it be using the 3? Or whatever value?
No,
you
why
give
did I
X?
write the squaring function using this notation? Why did I write cosine just COS, ln, ln, but I wrote the squaring function like this?
It's it's a parameter?
No, well, they're all parameters. That's a parameter. The h is the cosine function in this case. The h is the logarithm function in this case. The h is the squaring function in this case. We don't have a name for the squaring function. If you think in calculus, you always wrote the derivative of x squared. There was no squaring function. You always wrote out the formula. Mathematicians always write out x squared. Because it's such a simple function, they never gave it the name. So if I did something like this, that's not standard math. There is no, you never see the derivative of SQ is whatever. The squaring function doesn't really have a name. So I need something to say, do the squaring function. So that's why I wrote it this way. The cosine has a name, logarithm has a name. The cosine function has the name cosine. The logarithm function has the name logarithm. But the squaring function doesn't have a name, so you have to write out its definition. And if I just write this, that's not a function. Remember, we talked about that idea. That's not a function because it gets messier if I write something like this. You don't know what x, you don't know if that is supposed to be that could be x goes to x times y. That could be y goes to x times y. Then x is a global variable of constant. Now y is a constant. Now it's a function of two variables. I could plug 3 and 5 into the x and y. Remember, we talked about that idea. Expressions by themselves are never functions. That's an expression, but it's not a function. To make it a function, you have to say what are the inputs. Okay? X is the input. That means y is a constant. Is somebody better define? Somebody up here better say y is 6. On the other hand, if I do this, now x is the constant, so I better say up here what x is. On the other hand, if I do this, well, then I don't need a constant because this function takes in two numbers and multiplies them. And that function doesn't have a name. The function that takes in two numbers and multiplies them doesn't have a name, so I have to write out what its formula is. Okay? All right. So, and up here, I could change h so that h would be like this. See? Now h takes in two numbers. So it would take x and z and put them into here and here. And then over here, it would take z and 2 and put them into here and here. Okay, so I can make it look like that. But now this one won't work because cosine is not a function of two variables. So I'm kind of bouncing around with different examples. Now the cosine and the logarithm don't work because they're not functions of two variables. Okay, so think ML is motivated a lot by the way people think about math formulas. And it's not that surprising. Modern physics wouldn't exist without math, and modern physics is what our world's built on. Same with modern chemistry and all that. It's not so surprising that modern programming would start making more and more use of mathematics. It's something that a lot of people don't want to deal with, but programmers are going to become like physicists. Physicists don't do anything without math, and programmers in a few years will be about the same. There'll be more and more math will be part of programming. Why? Because we want to be able to prove that programs land airplanes correctly. You want to prove that a car will stop when somebody jumps out in front of it. When the car is finally driven by an AI, you don't want to say 99.9 times out of 100 it did stop when somebody jumped in front of it. Which is what AI does now. AI gives you a probability that the car will stop. And engineers know better than to say that the bridge will. Engineers don't give you a probability they give you a probability the bridge will collapse, but the probability is pretty close to zero. They know that the probability of a bridge just falling down is close to zero. We don't know that with the AI. The AIs right now are really horrible in that respect. We actually don't they just work most of the time, and nobody even really knows why. Okay, many times they don't. Many times they actually don't know why their AIs are working, and then they come really annoyed when they find a case where the AI will spectacularly fail. Okay, we want math proofs of our software eventually. We're nowhere near that, but this is the kind of thinking that's going to probably lead someday to be able to have software where we can prove that they do the right thing. So it's not surprising that math ideas would be kind of useful in programming. Okay, now down here, we got a simple, this is probably the simplest thing we could do to get this type. But like before, what we're doing is we're ignoring the rest of the list. So let's see if we can change this. Oh, well, first let me write it in using not, here I wrote it using, without using pattern matching. So let me write it again using pattern matching. So the way I would use pattern matching, I would say that this is y in front of y's. And then I'm going to take the y and the x. Okay. So if you give me a function and an x in an empty list, I need to produce a b item. Well, the x is a b item. The x is a b item, so I'll just spit it back out. Okay, because there's no a's in here to even put into the function. Okay, and I could then, I could just point out that the function is not even being used. On the other hand, if there's something in the list, well, then I'll take the thing from the list and the b item you gave me, the b item you gave me, and the thing from the list, I'll put them in H, and that'll give me out a b item. Okay, I'm not using what's left in the list, and I'm not using H here. Okay, this one's not a big deal, but this is a problem. I should be using the rest of the list. So let's see if we can figure out what to do to use the rest of the list. So let's make this a little bit, oh, now just double check. When I rewrote it using pattern matching, I shouldn't have, that should still be correct. Okay, still has the right type. Pair of an A-B pair, a function that takes an A-B pair and gives me a B, and a list of A's, and I'm producing a B item. Okay. Now, let's kind of think about this in terms of a picture. Fold L. There's a function, and there's a list. I'm going to call it, I'll write the list as A1, A2, A3, A4, okay? And then there's a B item, I'll call it Y. And here's what I'm doing. I'm basically saying, take this item here and this item here and plug them into H. Okay. Actually, I got them in the wrong order now. That should be, no, I'm sorry, A1. Oh, I'm sorry. I shouldn't change letters. This should be X. Okay. So I'm using X for the thing by itself. Oh, and I put the list in the wrong place. No wonder it wasn't making sense. There. So fold L, there's my function, there's my B item, and there's a list of A's. And a list of A's. And then what I'm going to do is I'm going to take what I did here is I took the first item out of the list, that's A1, the X you gave me, and that's all. And I'm not processing the rest of the list. Okay, so this is the B item. Okay, now this is a B. Now we want to think of a strategy that'll somehow, let's see if we can figure out how to use the second item in the list. Okay, like what can I do even with the second item in the list? Well, this is a B item. The function H takes a and a B item. So let me take the second thing in the list and apply the function to that now. Okay. Oh, Oh, I actually didn't write this I didn't use the pair notation. Let me go back a minute. H of the pair A1 comma X. Okay, see, it's H of the pair A1 comma X. Okay, now that thing is a B. This is a B. I can put a B item into the second part of a pair along with an A item. There's a pair. A2 is the second thing from the list. I take the A2, combine it with the H on A1 of X, and now I've got a new thing to plug into H. Okay, so now I've used up 2 items from this list. All of this is a B item because it came out of the function. Since this is a B item, this thing can become the second element of another pair. Okay, so take the third element from the list and pair it up with that B item. There's a new thing to plug, a new pair to plug into H. Now I've used up more of this list. Okay, now this is a B item, so now I can take the fourth A item, put it in a pair with this B item, and apply H to it again. This right-hand side uses up all 4 items in that list. So now I've got something that uses up 4 items in a list. Yeah, it doesn't use up everything in a list, but I see a pattern building up here. Okay. Once I've got an item out of the list and applied the function to it, I apply the function to the next item in the list with that result. Okay. Okay, here's how I want to write that. Here is the H, here's this guy here. Okay. What I want to do is, this is where the recursion comes in. I want to do this step now. I want to do one more step. Okay. One more step would be to say, oh, fold L with what? The, okay, now here I have to go here. I need an, let me see. Oh, I want to tell fold essentially what it is I want, oh, here's the way to do it. This is the new starting element. This is the new B. Think of this thing here as the new B item. So I'm going to call this function fold L with the same H, the new B item, which is H applied to what, which is using H one time. And then the list is what's left from pulling out the first item in the list. Okay. So this is what we did one time. That was here. See, that was one time. That just used up the list. That used up one thing in the list. Okay. Actually, I erased what we had earlier there. Okay. Here was dealing with one thing in the list only, the thing at the front of the list, but without pattern matching. Here's dealing with just one thing in the list, but with pattern matching. But once we've dealt with one item in the list, that should be enough of a clue to help us figure out what to do with the rest of the list. Okay, so this is what it looks like when we deal with just one item from the front of the list. Okay, the idea now is that's a B item. Make that B item this. So call foldl with the function h. Here is that B item. And then we take the rest of the y's and put them over here. So we tell foldl, do this again. What we did here in one step, we essentially say, oh, well, that is this middle parameter now. So we tell foldl, do this process again using what we just did on the first item in the list, along with the rest of the items in the list. So we've pulled one item out of this list, used it to build a new middle item, and then we have a shorter list, and we do recursion. Okay, so tell fold to use this function again on this new middle item and the rest of the list. So we're replacing this thing, which was initially given to us as x, with this. This replaces x. Okay. Okay. X gets replaced by this. H is just passed along, and the list is shortened. Okay. Now let's check. This should have the right type. Okay. Function of an A-B pair to B, a B item, an A list, and we get a B item out. Okay. And what fold, yeah, and here we see what fold is doing. It's building up a chain of operations on. Now, if you notice that what I did is I took this list here and reversed it. A1, A2, A3, A4. And I applied H to A1 with the starting value. That was a new starting value. And I apply H on H2 with that new starting value. And that becomes a new starting value. Then I apply H of A3 to that new starting value, and that becomes a new starting value. Then I apply H with A4 to that starting value. Okay, this guy is sort of a seed value. You start this process with that thing as the seed value. You apply H and the seed value once with one item from the list. That gives you a new item. That's your new seed value. Then you recurse with the new seed value on the shorter list. Okay, so there's the new seed value. You recurse on the shorter list. Here's the new first item in the list. H with the first item in the list and that new seed value gives you back a new seed value. You make that seed value, you pair it with what is now the first item in the list. Okay, because now you've peeled off the A1 and the A2, so there's the new first item in the list. You pair it with that seed value, and you get back a new seed value. You keep doing this until the list is empty. Okay, and then you've got what was the last seed value is your result. Okay. This is called folding because in a sense, this list is collapsing on itself. See, when you do that, you take a B item and an A item and you collapse them into a single B item. Then you collapse this into another B item. Then you collapse this into a B item. In a sense, the list is folding in on itself with producing B items. Okay. Another way to think about it, here's another way you can kind of think about it. I take the list, well, I'll do it here. I'm going to take the list A1, A2, A3, A4, and I reverse it. So it's A4, A3, A2, A1. I reverse the list. Okay. Then I pair A1 with my seed value. Okay. And I do something with them. Okay. So I'll just represent that with parentheses. I do something with those two. That gives me a new seed value. So then I pair that with this one. That gives me a new seed value. So I pair that with this one. That gives me a new seed value, and I pair that with this one. Now, how am I pairing things with a function h? So I'm really saying h of that pair, h of that pair, h of that pair, h of that pair. Okay, so take h of a1 and x, that gives me a new b item, make it the new right-hand side of another call to h. Make that the new right-hand side of another call to h. Make that the new right-hand side to another call to h until there's no more items. Okay, you're kind of collapsing this in from well, you're actually collapsing it. It's written this way, but it's actually starting with the first item in the list. It's actually taking this guy and combining it with this guy. Takes those two and combine them. Then after those are combined, it combines that with this one. Then after these three have been combined, it combines that result with this one. And after those have been combined, it combines that with this one. That's kind of, but it's written, it has to be written backwards like this. It's kind of, it's really notoriously confusing, but it's also notoriously useful. It's tricky, but it's very, very useful. Okay. All right. So this is fold L. Okay. It folds a list from left to right, but it's written in this funny way. See, it starts with A1, then A2, then A3, then A4. So it's really lurking from left to right. That's why it's called fold L, because it starts on the left. But it's done in a funny kind of way, so that it ends up looking like it's working from right to left, but it's you reverse the list before you do this formula. So this formula is written on the list, written backwards. So you're really working on the list, A1 first, A2 second, A3 third, A4 fifth, and any others. So you're processing the list from left to right using the H function. Okay. All right. So that's kind of a, now that's what fold L does. Fold R is going to do essentially the same thing.
I have a quick question.
Yeah.
Maybe it's not quick, but so the two or the three examples of fold L that you have, they all produce the same signature, correct?
Yes. Yeah. But
only the third one gives you the correct answer?
Yes, because it uses up the whole list.
Okay, that's what I was getting at. So if we have something like this on the homework, you were saying that we just need to find the simplest solution, not necessarily the... Okay.
Right. So if there's a list involved and you don't feel like using up the whole list, you don't have to. But if you want to try using up the whole list, go ahead. Yeah, because that would be good practice for thinking this way. But I did say in the problem that you could give me the simplest answer that works. What you can't do is ignore parameters. As we've seen several times, if you just try to ignore parameters, they don't end up with the right type. So by telling you that you can write as simple as answers you want, I'm basically saying you have to use all the parameters, but you don't have to use all the items in the list. Usually if you're not going to use all the items in the list, you just use like the first one, for example. Okay, so so that's how I'm thinking here. These are all the right type, but they don't use up the whole list, but they motivate the final answer. They kind of give me a sense of what I should do to use up the whole list. This used up only the first item in the list, but what I want to do then is recurse on that item. See, this guy here is that one right there. So what I'm really going to do is just say, oh, once I've got this B, just do the whole thing over again. Fold H on that new B with what's left of the list. Fold H on the new B with what's left of the list. That changes this one to something that uses the whole list. Okay? All right. Now, fold R kind of does the same thing from right to left. So fold R is going to take a list like this. And now what it'll be, fold R will be just put these things back in the right order. take X with the end of the list and apply H to it. That gives you a new end. Use it with H3, with A3, and apply H to that. That gives you a new B item. Use that B item with A2 and H. That gives you a new B item. Use that B item with A1 and H. So now you're working your way from right to left. Okay, over here. Now this one would be written again, just reverse this order. This would be A1 here now, A2, A3, A4. Okay, but the formula is going to change a lot. I mean, the idea looks like this. Fold R is like the symmetric version of fold L, where fold L reversed the order of the list and did this stuff from 4, 3, 2, 1 back that way. Fold R is just going to take the same formula, but kind of working from, well, the work is done from right to left because you do this inner H first. Remember, you always do what's inside the parentheses first. Since that is inside the parentheses the most, you do this one first because it's inside the most parentheses. So you're actually now doing the right end first. So that's fold R, okay? Whereas before, we were doing the left end first, A1. So that was fold L. We started with the left end of the list. Now the formula here is going to be, here's the formula down here. We'll just go, just look at the formula. The what I'm going to do is, I read this, okay, I read this from outer in, okay? Here's the first item in the list. So what am I doing? I'm taking H. Oh, let me change these to H's. I've been using H's, so let me change this to an H here. This is what fold R will look like. H of the first item. There's H of the first item in the list. Okay, so there's H of the first item. Now, what do I apply? Here's the other thing that goes into H. Okay, here's H of the first item, H of the first item. Here's the rest of H. That's the second parameter to H. That is fold recursively on the rest of the list. That's fold R with H, the same Z, the same, I didn't realize I changed letters from one version to the next. I can't use, change this to Y and Y's. So, okay, so that's Y and Y's. Okay, and then this is a X. Okay, there. Okay, okay. H on the first item of the list, H on the first item of the list. What's the other thing that goes into H? Okay, now the other thing that goes into H, here's the other thing that goes into H. What it is just fold R on the rest of the list. See, this thing's got the same shape as this whole thing does. Okay, this is just a shorter version of the whole thing. Okay, the blue part here is just a shorter version of this whole thing. So it's recursion. I take H of the first item of the list, then the second item in H is fold R with H and X and the rest of the list. Okay. Notice that the seed item is the same. The seed item on this guy, which is X, is the same as the seed item on this shorter list version. X is still the seed item. Okay. Notice that in the other one, we replaced the seed item. And the other one, the logic was that when you did the recursion, you replaced the seed item, the initial value, what's sometimes called the initial value of the seed. Fold L replace the initial seed value. Fold R keeps the seed value. Fold R does the recursion over here. Fold L did the recursion over here. There's slightly different kinds of recursion going on here. Okay. In the case of fold R, we get what to do by reading this formula off. We take the formula for fold L, reverse the order of the list. This is the formula for fold R. And then from that formula, we can read off what fold R does. It calls H on the first item of the list. And then we see in here the same pattern. Fold H on the same seed, but the rest of the list. Okay? Okay. And fold R and fold L have the same type. This is actually kind of an interesting thing, is if you, now from the point of view of types, remember we were guided by the type to write fold L, but I was kind of being a little bit leading here because the type for fold R is exactly the same. So we could go back and do this by type, and if we think a little differently, we can actually end up at this formula. So there's actually two formulas that give us that same type. This fold R and fold L have exactly the same type. They're built into ML. So here's fold L, and here's fold R. They have the exact same type. So that shows you that the type sometimes isn't, the type doesn't always lead you to the answer. In the case of fold L and fold R, there's actually two answers. There are two folds, fold L and fold R. They have the same type. They have that type. And we did it with one way of thinking down here. And I was kind of like pushing you in a certain direction in terms of the thinking. But if you go back to this type and you start over again, you can come up with a different answer. You can come up with this fold R answer. Okay. But I think the fold L answer is easier to come up with from the type. Fold L is a little bit easier to arrive at, I think, from the type, and fold R is a little harder to arrive at from the type. I'm not sure how people even thought of this stuff. It's pretty tricky. I mean, it's only 2 lines of code. Counting lines of code is not a good way to measure how complicated things are, even though a lot of companies will judge programmers on how many lines of code they write per day. Whoever first wrote these 2 lines of code, that's brilliant. Writing those 2 lines of code and writing and adding to it those 2 lines of code to give the 2 different folds is just brilliant. That's 4 lines of code that billion-dollar companies have been based on, because fold is really a powerful pattern. There's a lot of software that's built on the idea of fold. Okay, it's a very, very powerful pattern. Okay, let me see. What time is it? What time do we quit? I've lost track of time. Where are we in terms of time?
We're 1 minute over.
Yeah, we're running. Okay. Yeah, I have a timer sitting here, and I think I must have typed in the wrong thing into my timer. So we've explained fold L and fold R. We've derived fold L and fold R at this point. The next thing is to go through those examples of using them. That's where the homework, that's where the problems in the book come in. Okay, the problems in the book at the end of chapter 11 have a bunch of nice examples of how to use fold L and fold R. And we'll do a bunch of those on Tuesday. Okay, so I gave you 5 of them out of that list of 20 some. I gave you 5 as homework. We'll do a bunch of them on Tuesday. Okay, so you can start on the homework assignment, because remember the homework assignment, the first 4 are where I give you a type and you have to write the function. Then the next 2 are recursion. That stuff is not dependent on this fold R, fold on map, fold, and reduce. Okay, the last 5 problems in the homework are dependent on these problems on in the end of the chapter 9. So on Tuesday we'll do a bunch of the problems at the end of chapter 9, and that should give you a sense of how to do the 5 that were in the homework assignment. So you can get started on the homework assignment if you want right now and do the first 5 problems, 5 or 6 problems, and then you won't probably be able to do I mean, you can read the book. The book's supposed to be self-contained, but it's pretty tricky stuff. So you can read the book and you can give those problems a try, but we'll do a bunch of examples of using fold L and fold R and map. We'll do a bunch of examples using them on Tuesday. Okay, and that should be, then after you see examples of using them, you should be able to figure out how to use them in those 5 problems. Okay, it's tricky to define them and it's a little bit tricky to use them. Okay, they're not trivial definitions and they're not trivial things to use, but they're tremendously powerful. Not exaggerating when I say that huge amounts of stuff has been written just about fold L and fold R, and they're used a lot in big data processing. They form the backbone of a lot of the algorithms for doing data processing. Okay, well, we should quit there. Anybody got any question? Anybody got a question about this?
Will you be in your office hour today?
Yeah, in a half hour or so. Yeah, I'll be in the office hour.
Thank you.
Okay. Any other questions? Okay. If you have questions about the homework, send me emails about. If you have, you can download the homework and start. If you have questions about them, let me know. And we'll meet again. Have a nice weekend, and we'll meet next Tuesday. Bye.